Okay, good day again, class. So this is our second sample problem on the topic of unsteady state mass transfer, specifically unsteady state diffusion in various geometries. Now, the first sample problem was likened to a flat slab. The problem with concerning the agar with urea, and which was placed in a turbulent pure water solution. So the diffusion in that case was from the urea containing agar to the turbulent pure water. Now in this case, we have a different scenario in the second sample problem, and we have a very thick slab which has a uniform concentration of solute A of 1.0 times 10 raised to negative 2 kilomole A per cubic meter. And suddenly, the front face of this very thick slab is exposed to a flowing fluid having a concentration of 0.10 kilomole A per cubic meter, and it has a convective coefficient of 2 times 10 raised to negative 7 meters per second. Now, the equilibrium distribution coefficient, capital letter K, which is equal to the ratio of C sub Li to C sub I, is equal to 2.0. Now, we are to assume that the slab is a semi-infinite solid, primarily because of this particular phrase in here, a very thick slab. So since it's a very thick slab, then we are to assume that this very thick slab is comparable to the geometry of a semi-infinite solid. Now, having this assumption, we are to calculate the concentration in the solid at the surface. So we expect that our diffusion here, the mass transfer, should be coming from a phase of higher concentration to a phase of lower concentration. So if you're going to look intently on the problem, the initial concentration of the fluid, the flowing fluid, is 0.10 kilomole per cubic meter, whereas that of the very thick slab of uniform convection is 1 times 10 raised to negative 2 kilomole A per cubic meter. So in this case, if you're going to look closely, this one is just 0.01, while this one is 0.1. So our diffusion here will be coming from the flowing fluid to the thick slab, which has a uniform convection. So unlike the first sample problem wherein our diffusion is coming from the slab, but it's not a semi-infinite slab, a flat slab, and it is outwards towards the turbulent pure water where it is dipped into. So this one is the other way around. So our surroundings where our infinite or semi-infinite solid was placed into is of higher concentration than the solid itself. So the transfer of mass, that's the diffusion, is from the surroundings to the solid. So we are to determine the concentration at x equal to 0 right on the surface, and at x equal to 0.01 meter from the surface after 3 times 10 raised to 4 seconds, so equivalent to 30,000 seconds. Now, we are given also in the problem the diffusivity of the solid, which is 4 times 10 raised to negative 9 meters squared per second. So, for us to be able to solve this problem, okay, we need to write down the main formula, or we need to write down the direction in which we're going to determine the concentrations that are being required. So, we can do that by going to our board and see and plot out our direction in solving the problem. So let's say we'll start now with the direction in which we're going to determine the required information in the problem. So just like the first sample problem, this one is asking for the concentration. And if you're going to determine the concentration considering the geometries of the solid, then that would be only determined through y. So we need to determine the y. But in this case, there's no direct way of determining the y, which is dependent on the concentration variables. based on the formula appropriate for this particular problem. So in our case, we are given a semi-infinite solid because it's a slab which is very thick, the thickness of which is not even specified by the problem, so we can liken it to a semi-infinite solid. Now let's look into the figure which we can use for this particular semi-infinite solid. That way we will know how we get to find this y, which will lead us to the concentration. So if we go back to our slide, and this is our sample problem, if we go back to the figures that we have discussed before, the figure that is appropriate for this is this semi-infinite solid figure. And you can see that on the ordinate or in the y-axis of this particular diagram, we have 1 minus y. This one would lead us to y, which will eventually help us determine the concentration. But before we can get this ordinate, the 1 minus y, we need to determine the x or the abscissa, and we need to determine the values of the curves here. That way, upon projecting the value of the x upwards and resting on the appropriate curve value, we can read on the vertical axis the corresponding value of the 1 minus y, which will lead us to y, which will lead us to the concentration. So in this case, we need to know this one, the h square root of alpha t over k, and we need to determine the x over 2 square root of alpha t. But you have to remember, class, just like what I have discussed in the previous topic under also unsteady state diffusion on various geometries, that the figure that we are using is for conductive and steady state heat transfer. So the variables that are represented here on the abscissa, and that is on the x-axis, and on the curves will have its equivalent in the table that also I have shown to you. So we will go back to the table and find the equivalent expression of this h square root of alpha t over k and x over 2 square root of alpha t, and that is these two that we need to determine, so that we will be able to find this very important 1 minus y, which has also its equivalent in mass transfer. So we will go back to our figure before we go to the board. So in this case, this is our table. If you recall, we have this as the original heat transfer variable, and what I have read a while ago is h over k square root of alpha t, and the other one is x over 2 square root of alpha t. This one is for the abscissa, and this one is for the curve values. Now, we have two columns in which we're going to get its equivalent formula in mass transfer. And before we can do that, we need to identify the, shall we say, equilibrium distribution coefficient, and that's your capital letter K. In the middle column here, that is only for K equal to 1.0, and in the last column, we have for K values greater than 1 or other than, shall I say, 1 specifically. So we need to go back to our problem and check whether the K value that we have is 1 or other than 1. So our problem says that our K, our equilibrium distribution coefficient, is 2.0. So meaning we're going to use the equivalent formula in column number 3. So in column number 3 of our table, we have K values not equal to 1. So I need to get this formula, and I need to get this formula, because these two will represent my abscissa and the values of the curves respectively appropriate for the semi-infinite solid diagram that I have shown also to you, and that diagram is this. Okay, so now we go back to our board and write down the formulas that we will be using. Now, for me to be able to get the y, I need to get the abscissa, And the abscissa in this case, I have shown to you already, is x over 2 square root of alpha t. However, its equivalent in mass transfer is x over 2 the square root of the product of the molar diffusivity and the time for diffusion. Now, the other formula that we will write down here so that we can get the things that we will be needing is the formula for the curve. The original curve equation is h over k, and it is to be multiplied to the square root of alpha t. Now, if it's to be used for mass transfer, the equivalent formula for this is capital K, K sub c, the square root of the product of dA t over dAb. Okay. So we need to find these two for us to be able to find the 1 minus y specifically based on our figure. Now, we will check based on the problem what we have in terms of the information and what we still do not have. So, we have been provided with the molar diffusivity, the time for diffusion, and this goes with here as well, and this, and we're given the equilibrium distribution coefficient, and we're also given the mass transfer coefficient. So everything is given except for the x in here that appears in the numerator of the formula for the abscissa value that we're going to use. So we're going to draw the slab as described in the problem, and it's an infinite slab. So we don't know how thick is this, as long as it's a very thick slab, an infinite slab. And this is where the mass transfer is going to occur, starting from, so this is your bulk solid, and it's going to transfer towards your semi-infinite solid. So your bulk solid, as mentioned in the problem, has a concentration. So we know that the direction of diffusion is from the bulk liquid. It's because this one is of higher concentration. So this is 0.10 kilomole per cubic meter, whereas this infinite solid is only 0.01 kilomole per cubic meter. And since our transfer will be from this bulk liquid to the solid, then the initial point where mass transfer is to commence is this, and at this point at the surface your x is equal to 0. Now there are two scenarios as stated in the problem, and that is, one scenario is you are to determine the concentration here at the designated time. So let's say the concentration at x equal to 0 is C prime. Okay, and the other requirement is that we are to determine the concentration at a point which is stated in the problem 0.01 meter from the surface. So this is your, let's say this is your x. So I'll say here x C prime for x prime equal to 0, because we're starting our diffusion from the surface. And since I have labeled this as x prime and C prime, so I will label this as x double prime, and this concentration will be C double prime. So I'll get the 2 there. Okay, so these are our labeling. So for here, you have the x here equal to 0.01 meter from the surface. Okay, we are to determine the concentration. The other one is we are to determine the concentration right on the surface at the time designated in the problem. So now we will first start with this particular scenario, because this is the first thing that is mentioned in the problem. So to check, let's say, what's the unknown? So we will know which one we need to solve first, calculate the concentration in the solid at the surface. So we need to first determine this, followed by the second scenario wherein x is equal to 0.01 meter from the surface. Okay, that's what we're going to do. So we'll start with that on the surface. Okay, so letter A, we'll write here letter A at the surface. And this is for x equal to 0 because it's right on the surface. Now, our formula is x over 2 square root of dABT. So, we will determine this first. Our x over 2, the square root of the product of the molar diffusivity and the time for diffusion. Now, you could see already that at the surface where diffusion commences, it's x equal to 0. So, this is already 0. Okay? This one, the x over 2 square root of dABT is actually the abscissa for the figure that we're going to look into later. The next is for the curves. So, our curves will have this particular formula. So, we'll have the capital K, the small letter k, the square root of the product of the molar diffusivity and the time, and again divided by the molar diffusivity. So let me check if it's the correct formula. So that's it. Then what we're going to do, we will substitute the values that are stated in the problem. Now the problem says that our equilibrium distribution coefficient, the capital letter K, is 2.0, and our mass transfer coefficient is 2 times 10 raised to negative 7. I will not anymore write the units. Anyway, I'll make sure that all my units are SI. Then I will multiply this to the square root of the molar diffusivity, 4 times 10 raised to 9, and the time, which is in seconds. And the time is 3 times 10 raised to 4. Now, your denominator for this will be 4 times 10 raised to negative 9. In this case, the value for this curve equation will be 1.095. So that's the value for our curve equation. Now, using this value, the curve equation, the 0, then we go back to our figure and determine the corresponding value of 1 minus y. So the values we're going to use is for the x, we'll have 0, and for the curve that corresponds to this, that would be 1.095. Then we go to our figure and use this particular value. So let's see what we'll be getting for the 1 minus y. So this is our semi-infinite solid, and we are going to use this as 0. It's 0 because our x is 0 at the surface. The corresponding value for the curve here, as given in the solution a while ago, is 1.095. So I'll simply go up from the 0 here, and my 1.095, if this is 1 and this is 2, it would be more or less 1.95, somewhere here. I like to say it's somewhere here. Okay? This is 2 and this is 1. So more or less our 1 minus y has a value of, this is 0.6 and this is 0.8. 0.7 somewhere in the middle. This one, 1. 0.7 here, 0.77, 0.72 or 0.75, depending on how you're going to read it. So let's say we'll use the value that is given to us in the guide, in the book, and the value for that is 0.62 only. the 1 minus y is 0.62 because this is for the 2. Your 1.95 might be in here. But if I'm going to read it from here on my end, that would be around actually it's already 0.7, right on the middle, a little bit higher than that, so 0.7 something, 0.75. So actually it really depends on the way you take it from the graph. So let's say we're going to use the value of 0.72. Like to use that one. So we'll have here a 1 minus y of 0.72. Now a 1 minus y of 0.72, that would be 0.72, has an equivalent formula for mass transfer of C minus CO all over C sub 1 over K, the equilibrium distribution coefficient, minus CO. Now, I'll show to you that this is really the equivalent for 1 minus K in this scenario. So, we'll go to our table again. For a value of K that is not equal to 1, our 1 minus 1 is this. So, this is the formula that I have written. This is the formula that I have written in the board. Okay, the C minus CO over C sub 1 over K minus CO. So, we will go back to our board. And this formula. So, now we're after for this C. Now, we will just need to substitute everything so that the only remaining unknown there is the C. So, we'll have a 0.72 on the other side. And you have a C. Your CO is the concentration of the infinite slab. And that's 0.01. Your C sub 1 is the concentration of the bulk liquid where your mass transfer is starting from. So, 0.10. Divided by the K, which is 2.0, minus again 0.01. So, in this case, you'll be getting a value for the concentration at the surface after 3 times 10 raised to 4 seconds. And that would be equal to 3.48 times 10 raised to negative 2 kilomole A per cubic meter. Now, you will use the same procedure when you will now be using, instead of 0 for the X, you will now be using a value of 0.01 in here, in the second scenario, so that you will have a new abscissa. So, we will do that. At X equal to 0.01 meter from the surface, your formula for the abscissa, which is X all over 2 over the square root of the product of DABT. So now you will have a 0.01 here. We divide by 2 the square root of our DAB and the time, which is 4 times 10 raised to negative 7 times 3 times 10 raised to 4. Okay, so you will have an abscissa value in this case being equal to 0.457. Okay, 0.457, and you will have to determine the other value, which is for the curve. In this case, this does not change, class, because there's no X here. So the only thing that changes is the abscissa value, but the curve value is the same. So your curve will be still 1.095 in the second scenario. So your curve value, or that would be the K over K sub C square root of D sub ABT over D sub AB is still equal to 1.095. So you will use these two values rather, this one and this one, to find the 1 minus y in the graph again. So you have 1.095 and 0.457. So we'll go to our curve and find that value, 0.457. If this is our 0.4 and this is our 0.6, our 0.5 is here and 0.457 is somewhere in the middle. So it's just like dividing the space in between 0.4 and 0.6 into 4. That would be the same for the curve. And that would be 1.095 in here, 1.095, but it would be 0.457 in here on the abscissa, not on the curve. So this is 0.4, this is 0.5, 0.6, 0.7, 0.8. So 0.457 is somewhere in the middle. I'll go up until I'll reach the 1.95, and it's somewhere here, 0.35. On my reading, it's around 0.35 or 0.34. 1.095. Okay, it's not 1.95 but rather 1.095. So that explains why my value was so high a while ago. 1.095 is a little only above 1. So it's a little above 1 only. 0.4 here, 0.45. So it's 0.25 or 0.26. My 1 minus y is 0.26. 0.45, I'll go up and then it's somewhere here. There. So 0.26. And now, we'll go to our board and we'll have this one as 0.26. And this will again be equated to the same formula here in the first scenario. So you will have C minus C sub O over, again this is C sub O, C sub 1 over capital letter K. And your C is still unknown. Your C sub O is still 0.10. You will have here, your C sub O is not 0.10 but rather 0.01. So this is 0.01 and this is 0.10 over 2 minus 0.01. You will have a concentration value here which is equal to 2.04 times 10 raised to negative 2 kilomole A per cubic meter. In the previous, I was reading a value of 1.95. It's actually 1.095. So this one is not 0.72. But if we go back to our curve, it's like just a little bit above here. So that would be 0.62, not 0.72. So 0.62 that is. So we'll go back and change the value that we have substituted. So 0.62 here. So we have 0.62 and the next would be also 0.62. So this is 0.62 and we will have a value here of 3.48 times 10 raised to negative 2, more or less. Okay, so we have determined, in this case, we have determined the concentration. So this one, the concentration right on the surface at 30,000 seconds. And this one, the concentration 0.01 meter from the surface. Okay, we expect, of course, that over time the concentration in the surface will be still greater than the concentration somewhere away from the surface, because our diffusion is starting right on the surface. So over time, we expect that a distance from the surface will have lesser concentration than that on the surface. So in our discussion a while ago, this is our C double prime. That's x distance, that's x double prime distance from the surface, and this is our C prime. This is right on the surface, all measured at the same time interval, which is 30,000 seconds at the start of the mass transfer. So this will be now your complete for now, and then I suggest that you look for other problems on different geometries, other geometries than these two, and practice solving on unsteady state diffusion based on those other geometries.